So we're looking at a carbocation methyl shift. So the biggest thing is there has to be carbocation formation in the first place. So if I draw something like this, right? So for there to be a methyl or hydride shift, there first has to be a carbocation, right? So bromonium ions do not form carbocations. BH3 does not form a carbocation. Right? Palladium on carbon, H2, does not form a carbocation. The only things that form carbocations, right, are HCl, right, or HBr, those strong acids, or H+, right? So first thing is, to have a carbocation rearranged, we have to make a carbocation. Right? So the first step here, what's our nucleophile, what's our electrophile? Pi bond is the nucleophile. Right. Forgot to number the carbons, as we should always do.
Does our hydrogen always go on the most substantial?
So I always like to think about what carbocation should we form. So if I number my carbons again, 1, 2, 3, 4, 5, 6, and 7. I have a choice, right? The pi bond was between carbon 1 and 2. Where do I want to put the plus charge?
2.
On 2. Why?
Secondary carbocation?
It's a secondary carbocation, and why is that better than a primary? And why is that better?
There's hyperconjugation.
More hyperconjugation, that's right. So we put a plus charge here. We also made Cl minus. Now at this point, that's fine. But carbocations will always rearrange if they can form something more stable. So you always got to ask yourself, every time you make a carbocation, you got to say, can I form a more stable carbocation? Now, more stable, that means you can't go from, if I have a secondary carbocation, can I make another secondary carbocation? Will it do that?
It wouldn't make a difference.
No, that's a lateral move, right? We always want to go downhill. So in this case, can we make a more stable carbocation? Yes. What kind of shift are we going to have?
Hydride shift.
A hydride shift, right? So don't forget, remember, H's aren't drawn in. Sometimes you have to draw the H's in, right? So don't let that confuse you. So in this case, right, the H shifts, right, the two electrons there between that carbon and hydrogen, both those electrons go the H to that carbocation.
Was that H originally on carbon 1?
That H was originally on, has always been on carbon 3, right? Carbon 3 has always had an H. I just hadn't drawn it until now.
And then carbon 1 has an H.
Carbon 1 got a new H, right? It started out with 2 H's, and now carbon 1 has 3 H's. And one of them came from the HCl. Good. So now what do we have?
Sorry.
Plus Cl minus. So here's an interesting question. Why does the hydride shift happen faster than the chlorine attacking the carbocation? Because doesn't the chlorine want to attack the carbocation? Why is this 1 to H shift faster than the chlorine attacking? What do you guys think? Well, that's more stable. That's one reason. Yeah, it's you form a more stable carbocation. But why do you think it's? I'm telling you, the rate from going from 1 to the shift is a faster rate than the chlorine attacking. Why is that? Do you think?
Chlorine is a lot bigger versus.
Hydrogen smaller.
Hydrogen's smaller. Yes, you're talking about size. Okay, you're getting close. You guys are getting idea. You're thinking about right. I like that idea.
Electron, no. Isn't carbon 1?
Let's think about it. What do you need? What do you need to have for a reaction to take place? Right. You need concentration. So things need to be concentrated. You need the orientation. Right. You need sufficient energy. H is closer. H is in the same molecule, right? Is it easier for me to punch myself than to ask somebody else punch me? Yeah?
Yeah.
Right? Right? It's a lot faster, right? 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 An intramolecular reaction is much faster than an inter. Is it easier for one molecule just to have its own action happening in itself versus having to get two things running into each other? Absolutely. Right? So then the chlorine attacks, and we get the final product. How many steps was this reaction? Every arrow is a step, right? Every arrow is one step. So how many steps were there? How many hills were there? 3 steps, 3 hills. Right? Let's maybe make a little quick free energy diagram even. So how high should the first hill be? Super high. Why? Because we're making that carbocation transition state. Should the second carbocation be lower or the same energy as the first one? Lower, right? Because we're making a more stable one. And then the final step is going to be really fast. And I don't know if the product's more stable than the starting material. That's not, don't worry about that. But you see that? So there's every hill, every reaction arrow gives us a hill, a step. And every one of these carbocations is an intermediate, right, along the way. So we have transition states, 3 steps, 2 intermediates.
First, like when the pipeline attacks the electric file,
So let's talk about stereochemistry now, this problem. So, what's the hybridization state of a carbocation? sp2. So let me draw a little sp2. Right? And whatever this is, or this is, or this is, right? So this p orbital is empty, right? There's a plus charge. Is there a preference when this chlorine attacks? This chlorine attacks right here. Does it care if it attacks the top or the bottom? But if it attacks the top, doesn't that give you 1 enantiomer? And if it attacks the bottom, it gives you the other enantiomer, right? So what you're going to get here is a mixture of both R and S, and there's no preference, so it's a 50-50 mixture, and we call that racemic. Right. Good question. So what if I put a what if I put a methyl group right here instead it was wedged? So there's a stereo center there now, right? And this stereo center is always going to be, let's say it's R. So in the product, I made this. So what kind of products have I made? What kind of products did I make? If I already had one stereo center there in the molecule, and I made this new asymmetric center that's half the time it's R, half the time it's S, I just created diastereomers, right? I could have RR or I could have RS. And diastereomers, do they have the same physical properties?
Except for interaction.
Except when interacting with chiral environments. So diastereomers have different physical properties, right? We can diastereomers have different physical properties. Enantiomers, right, have the same physical properties. So just by adding this one stereo center, I can change them from being a racemic mixture to a diastereomeric mixture, right? So this is if I added this stereo center in, instead of making a racemic mixture, I make diastereomers. Pandora, yeah. Okay, so let's talk about stereo centers and the umbrella that is the stereo center. Stereo center exists at the top. There's just two different types. There's the cis-trans types, where both of these carbons are stereo centers. What that means is, if the elements, the functional groups, the things that are attached to this carbon were to switch places, we get the other stereoisomer. So this is a cis molecule, the other, or Z molecule, the other stereoisomer would just be E, the trans. Very good. Right? So both these carbons are stereo centers. They're cis-trans stereo centers. The other type of stereo center that we can have is with an sp3 hybridized carbon that has 4 different things bonded to it. Right? These things can be either R or S. Right? These are enantiomers. And within enantiomers, there's enantiomers and diastereomers. There's also meso compounds. Right? So don't forget those things as well. So there's two types of stereocenters, cis-trans and these asymmetric centers as well. Okay.
Wedges or hashes?
Yeah, I'll show you.
Do it on the one you just drew for the asymmetric center.
Well, no, I'm gonna draw a blank one. I'm gonna draw a blank. I'm gonna draw a blank.
Oh my god.
I'm gonna draw a blank. OH.
Anything wrong?
All right, so it's just blank like this, right?
Yeah.
So the first thing you need to do is rank them, right? So let's rank them. So the easiest thing to do is find the lowest or the highest. So which one's the lowest?
Four, I mean eight.
4, and what's the highest?
Oh.
Oh. What's number 2? This is 2. Good. And let's say I want you to make this R, right? All you're going to do is grab your R model,
Red, white.
and red, white, and blue, and make it. Just make this. So in this case, if I want to make it R, I would,
So you make
I can do this off the top of my head. OH and dash is H. That's R. Right? If I want to make the S, I would just switch around the H and the OH. I'd get there.
That's what it said.
And that is how you do it.
I'm the person that will be like there with my mom, like, help me.
So let's look at one. Let's look at an example. How can we tell if this is RS?
Oh, I got an example that threw me off.
We'll look at one. So let's first thing we gotta do is what? We gotta do rank them, right? So which one has the lowest ranking? The OH has the lowest ranking here. Right? What's the next low? What's the highest? What's the highest? Oh. I is the highest. What's the next highest? F, and then 3. So if you did this, remember 4 is always going to be green, right? So 4 is always green in our little scheme. Red is always 1. White is 2. And 3 is blue. So literally, you have your R model and your S model. And you basically got to turn it till you get it to look like this. So you want to have the white ball coming at you, the blue one going away from you, and the other two in the plane. And that would either tell you this is R or S. So what do we have? I know what it is already. So white is coming at you.
Is it? It's R, right?
Yeah.
S is red.
Isn't it R?
I'm a mile.
Blue is coming away from you. Blue is going away, and white should be coming at you. And then red should be pointed up. But now, right? But now, on your right hand side should be the 4. Green should be 4 to your right hand side. And you need, yep, R is clockwise. So once you get the picture drawn right, you grab the green ball and you turn it towards you, and you go red, white, and blue. In this case, it's R. So this is a homework problem. And it kind of leads into that first problem we worked on, where we're going to go through a carbocation intermediate. If we go through a carbocation intermediate, is the reaction going to give us a mixture of enantiomers or just one enantiomer? It's going to give us a mixture. right? So let's just walk through the mechanism. So the first step, a pi bond is the nucleophile. It attacks the H. We got to make a decision. We should number our carbons first. 1, 2, 3, 4, 5, 6, and 7. We broke the pi bond between carbons 4 and 5. So we got to decide where we're going to put the carbocation. Which carbon should have the carbocation?
Or,
Four.
doesn't matter.
Doesn't matter. Oh, no, does it matter?
It doesn't.
Does it?
No, it doesn't matter.
Yeah, it does.
No, it doesn't.
5 has an H, actually.
It can be either
It's all
or.
over.
Yeah, it's always. So after much discussion, we decided on 4. 4, of course, is more substituted. This is a methyl, not an H. Remember, don't forget that. We also make Cl minus. But again, this comes down to the question: what's the hybridization state of a carbocation? sp2. So let me draw the picture again for you. So I'm very good at it. Yeah. Right? Plus charge there, right? Is there a preference for the chlorine to attack the bottom or the top? Nope. So we're going to get both products, right? So we're going to get the chlorine attacking. So we're going to get both enantiomers. So this is tough because we got to draw both enantiomers then. Because we're forming a stereocenter. We're forming not a stereocenter, not just a stereocenter, we're forming an asymmetric stereocenter. Ooh. So the easiest way to do that, I think, is just to draw this like that, right? Draw the methyl wedge and the ethyl hatched, and then do that twice.
Doesn't matter
Watch.
what you choose to do.
Watch and learn.
You'll
Nope.
mess it up.
You'll never mess it up.
The CO should be.
So the Cl can either be at the top, right? Or it could be at the bottom. And these are both different enantiomers now. And if you're not positive, check it. All right, let's look at a problem where we have, say, H plus, and then we have CH3OH. So like every reaction we do, we got to ask ourselves, what's our electrophile, what's our nucleophile? So the problem with this is now you have 3 things. Most of the reactions you only have 2. So if you can figure out one, you can kind of guess what the other is. So again, we want to find the extremes though. So which one of these do you think is the most electrophilic? Right, which one's the most delta plus, the plus charge thing, right? So that's for sure the electrophile, right? So the book might show actually methanol attacking this and getting protonated, but we can skip that step, I think, and just show the pi bond attacking here, right? Number our carbons, 1, 2, 3, 6, right? What carbon should have our carbocation? Carbon 2, I think. That's good. 1, 2, 3, 4, 5, 6, 7, and 8. Now, are there any? So we formed a carbocation. We also made Cl minus. We know that we have a bunch of methanol floating around too, right? Below the arrow means it's our solvent. Right? It's an alcohol. And either an alcohol or water, we should be thinking about the solvent might come into play. Right? Alcohols or water.
Yeah, we're using CO minus, it says H.
Oh, sorry, my bad. Yeah, there's no, where did I get that from?
He's just up here.
Where did the H plus go?
You cannot create, you shall not create stuff. Oh, there we go. Get that. Right, balance our charges. We had a plus charge in the starting materials, we should have a plus charge in our products. So, if we form a carbocation though, can we do a rearrangement here?
But it wouldn't be.
What rearrangement can we do?
Secondary to secondary.
Remember, to do a rearrangement, so a lot of people want to say, well, there's a hydrogen here, right? But how many bonds away is that hydrogen? Is this hydrogen doing hyperconjugation with this carbocation? Right, here's the carbocation. Hyperconjugation is how many bonds away?
3 bonds away.
Two,
I thought you said 3.
two, two bonds away. So it's the hyperconjugation buddies are the ones that can actually do the shifts. So if you're not doing hyperconjugation with a carbocation, you can't do the shift. So if you're 1, 2, 3 bonds away, can you shift?
No.
No, it's too far away. So you can't shift here, right? Too far away. Orbitals have to overlap.
The carbocation is on 2, isn't it?
Carbocation's on carbon 2.
So it can't go 4.
Could I shift to 3?
Yeah.
But why would I shift to 3 though? What kind of carbocation would I form? What kind of carbocation is 2? I don't move laterally. I only move downhill.
It's 2 away from 4.
It's 2 away from 4. It's 1, 2, 3, or 2 bonds away from 4.
Yeah.
It's not gonna work. Not gonna happen.
Why?
Because it's not close enough to do the shift. It has to be 2 bonds away. The MTP orbital, right? Bond.
It's 3 from the hydrogen.
It's 3 from the hydrogen. 1, 2, 3. It has to be 1, 2 bonds away. Good. So the key point here, though, again, is just another layer of, right? Another layer of understanding what our nucleophile is, right? So now our alcohol, our solvent, because it's so prevalent, even though it's not a great nucleophile, is going to attack the carbocation. And again, is it going to attack the carbocation from the top or the bottom? Both. Are we going to form an asymmetric stereocenter in this product?
Yes.
Yeah. So if we have to show both pictures, what kind of mixture are we forming then? A racemic mixture, that's right. So this can be either way. And this is where people screw up. They want to, for some reason, break the carbon-oxygen bond here. I do not know why. Right? These electrons moved and attacked there. Nothing happened here. Nothing happened here. Right? When you have an alcohol as a solvent, you end up getting ethers as products. And don't forget our plus charge. So the last step, regenerate the H plus. Right? We could say the H plus was a catalyst. Right? A cat. Yeah. O, CH3. Right? And we'd say it's racemic, right? We get both R and S. Yeah. Okay, so let's look at a bromonium ion situation. And let's say we're in water this time, right? So the first step here, we got to identify our electrophile and our nucleophile. So remember bromine, Br2, because bromine's so large, right? It's lower on the periodic table, it can have its own self-induced dipole, where it's like flipped, yeah. Where it's like a roly-poly, right? You can imagine all the electrons kind of swishing around. And so at any one point, one of the bromines is slightly delta plus, so it's a decent electrophile, right? So of course our nucleophile is our pi bond. It attacks the bromine. And then we got to remember, another lone pair from the bromine comes back in and attacks. It's a 3-arrow deal, right? We form a bromonium ion. We make a bond, we break a pi bond, we break a Br-Br bond, and then we make 2 bromine carbon bonds essentially in this process. Let's number our carbons: 1, 2, 4, 5. So the reason why the bromine comes back and attacks is so that we don't form a carbocation. We will not form a carbocation in this, and that is key. So imagine the bromine is up here at the top. H's are coming out at us, and the rest of the ring is going back. Now, what was the hybridization state of alkene or carbon 1? What hybridization state is carbon 1? How many pi bonds does it have?
Oh, I see 2.
So if it has 1 pi bond, it has to have a p orbital, so then it has to have 1 p orbital, so it's sp2. Carbon 2 is also, what's the geometry of an sp2 hybridized carbon? The geometry.
Oh,
Trigonoplanar. So is there a preference where the bromine would end up on the top, or could it end up on the bottom? Is there a preference? No. So you actually make two. Oops.
But in step 2, it's not trigonoplanar, like what you're doing right now, right?
No, it's no longer trigonoplanar now. Now it's tetrahedral, but right. So you see, you can have two different types of intermediates here, right? And both of them have Br minus, right? So you have two different types of intermediates here. They both have Br minus. But don't forget, right? We're in water. So how much more water is there than Br minus at any one point?
A lot more.
A lot more. Right, so water is going to, even though is water a better nucleophile than Br minus? No. It's just a matter of concentration, right? And now where is it going to attack? Where is sigma star for this carbon-bromine bond at? On the other side of the ring, right? So we attack sigma star. We attack the antibonding orbital of this bond. If you put electrons in an antibonding orbital, what happens to its bonding orbital? It breaks, right? And that's important because we've got to see where it attacks, right? So I'll show one example. And why is this important? Because this is going to affect, right, the three-dimensional orientation of the product, right? The bromines end up being what to each other? What relationship? They're always going to be trans, right? So the bromines will always be trans. And you'll form both stereoisomers, right? So if I did the exact same, oh, what have I done? Why didn't have somebody stop me?
I was going to.
What have I done?
What's wrong with it?
What have I done?
Why'd you write bromine?
I don't know why I wrote bromine.
This doesn't make sense.
My bad, bro.
Okay.
Ah,
Could bromine not bond there?
No, because there's more concentration of H.
there's more water.
So
So it could, but it won't.
It could, but it's less likely. Sorry, fixing it.
H2O wasn't there.
Great. Thanks.
Thank you. And the final product, we're going to make a racemic mixture.
Is there really coming?
We're gonna make a racemic?
Yep,
What?
yep.
Can you explain that?
Because they're always going to be trans to each other, right?
The OH?
Yep, so I'm going to get both stereoisomers of this. So I'm going to get either the,
How are they always trans to each other? They can't be cis?
they can never be cis, right? Because where's sigma star?
It's down on the lower left.
So it's always going to give us a trans product. Because sigma star is on the opposite side
I
of the
know
ring.
that's sigma star, yeah.
How do I know?
I just memorized.
So the reason you know that is because in the products you get are always trans. So we can do NMR to see, right, is this a cis or trans product? And so it's experiments. They know it. They always get the trans. So it's not because like they predicted it. It's because they.
Is this the only one that they're always going to be trans in? Is it sigma star?
Chlorine 2. Chlorine 2.
But in this same trigonoplanar, right?
Yep, same idea. Yep.
Is
So there'd
sigma
be-
star, does that only show up in trigonoplanar, Wenzel?
No, sigma star shows up in everything. Right?
Can you tell?
Technically, this right here attacked sigma star here and broke this bond.
Okay.
So the antibonding orbital is always important. If you put electrons in anytime you break a bond,
You're gonna make one.
that means you put electrons in that bond's antibonding orbitals.
Should the bromine be on the bottom?
I'm so dumb. I've forget this whole mess up here. I screwed it up. My bad. I'm getting tired. No, that could have happened too.
How was that right?
The biggest point to be made here. Biggest point to be made here is you always have trans products, and that water or the solvent can be the nucleophile. And also to remember, there's 3 arrows that need to be drawn. So don't worry about this right now. Forget about it.
What about the first one?
Worry about the first one and understand how that happened.
Does the second bond, the Br triangle thing, does that bond break in those electrons with the bromine in, right?
Yes. So these electrons right here went to the bromine.
Okay.
Absolutely.